everyone, welcome back to the Mojo-GPU puzzle series. Today we're tackling puzzle 3, guards. This is a fundamental puzzle that teaches you one of the most critical concepts in GPU programming, preventing out-of-bounds memory access. In this puzzle, you will learn how to safely handle situations where you have more threads than data elements. This might seem simple, but it's a pattern you'll use in virtually every GPU kernel you write. By the end of this video, you'll understand a few key concepts. First, how to handle thread to data size mismatches. GPUs launch threads in fixed block sizes, but your data might not perfectly align with those sizes. Second, how to implement boundary checks to prevent out-of-bounds memory access. Writing past array boundaries causes undefined behavior and crashes. And third, the pattern of conditional execution in GPU kernels. You'll learn when threads should execute and when they should skip their work. These concepts are absolutely foundational. Every production GPU kernel uses these patterns in some way to ensure safe, correct execution. Let's define some key terms. Thread index, represented by threadindex.x, is the unique identifier for each thread within a block. Think of it as each worker's employee number in our parallel workforce. Guard condition. This is an if statement that protects memory access. It's like a bouncer at a club, only letting threads through if they have valid data to process. Out-of-bounds memory access. This occurs when a thread tries to read or write memory outside the valid array range. It's one of the most common bugs in GPU programming and can cause crashes or corrupted data. Conditional execution. This is when threads selectively execute code based on conditions. Not all threads do the same work. Some may skip operations entirely. The key insight here is that the GPU threads are cheap to launch, so we often launch more than we need and use guards to control which ones actually do work. Let's visualize the problem we're solving. Imagine you have an array with size equals 4 elements, but you're launching thread blocks with 8 threads. Why? Because GPUs work most efficiently with specific block sizes, often powers of 2, like 32, 64, in our case, 8 threads. Really, 8 threads is too small a block to make optimal use of GPU architecture. 64 is a much better minimum, but this small block size is helpful for learning examples. Here, threads 0 through 3 have valid data to process. Thread 0 processes array index 0, thread 1 processes array index 1, thread 2 processes index 2, thread 3 processes index 3. But what about threads 4, 5, 6, and 7? They don't have corresponding data. If they try to access memory at indices 4 through 7, they'll be reading and writing beyond the array bounds. Think of it like this. You have 4 desks in a room, but 8 workers show up. 4 workers have desks and can do their job. The other 4 need to recognize that there's no desk for them and just wait. The mathematical operation is simple. For each valid thread I, we compute output at position I is equal to input A at position I plus 10. But the critical part is if I is less than size. This guard ensures that only threads with valid data indices execute the operation. Without guards, those extra threads would write to invalid memory locations, causing undefined behavior. Your program might crash, corrupt data, or appear to work but produce wrong results. This is why guards aren't optional. They're essential for correctness. Let's check out problems P3, P3.mojo. Let's look at our starting code structure. First, we have our configuration constants at the top. Size gets 4, blocks per grid gets 1, threads per block gets 8, 1, and dtype is dtype float 32. Notice the mismatch here. Size is 4, but threads per block is 8. This is intentional. We're creating the exact scenario where we need guards. Here's our kernel function signature. We have 3 arguments, an output array pointer, an input array pointer, and the size of valid data. The pointers are unsafe pointer types. Unsafe because we're responsible for the bounds checking. Inside the function, we already have I gets threadindex.x. This gives each thread its unique index. Thread 0, I gets 0, thread 1, I gets 1, and so on up to thread 7. Then we have below this comment where we need to implement our guard logic. Below in the main function, you can see the test setup. We create 2 buffers, initialize the input array with values 0 through 3, launch our kernel, and then verify that the output is 10, 11, 12, 13, which is the input at each position plus 10. The expected output shows what we're aiming for. So for our 4 elements, 0 plus 10 is 10, 1 plus 10 is 11, 2 plus 10 is 12, 3 plus 10 is 13. Now let's implement the solution. We need roughly 2 lines of code. First, let's think about what we need. a guard condition that checks if our thread index is valid. I'll type out the if statement. If I is less than size, this is our guard. We're asking, is my thread index less than the actual data size? For threads 0 through 3, this will be true. For threads 4 through 7, this will be false. Now inside this guard, we put the actual work. Output at position I is equal to input A at position I plus 10. And that's it. Let's trace through what happens. Thread 0, I get 0. Is 0 less than 4? Yes, so it executes. Adds 10 to 0, that's 10. Thread 1, I is 1. 1 is less than 4, so it executes. 1 plus 10 is 11. Thread 2, 2 is less than 4, so it executes. 2 plus 10 is 12. Thread 3, 3 is less than 4, so it executes. 3 plus 10 is 13. Thread 4, is 4 less than 4? No, so it skips memory access entirely. Same with 5, 6, and 7. They all skip. Each of those threads is more than 4. The beauty of this pattern is its simplicity. 2 lines of code protect us from undefined behavior and crashes. One important note from the puzzle description, your code might appear to pass tests even without the guard, but don't be fooled, that's just undefined behavior. Just because it doesn't crash doesn't mean it's correct. In Puzzle 10, we'll learn about GPU sanitizers that catch these bugs. Let's test our solution. In the terminal, I'll run pixi run p03. Perfect. Our output matches the expected values exactly. All 4 elements have been correctly incremented by 10. Let's review what we learned. Thread data mismatches are normal. GPUs launch threads in fixed block sizes, so you'll often have more threads than data elements. Guards prevent undefined behavior. Always check if I is less than size before memory access when thread count exceeds data size. Conditional execution is efficient. Inactive threads simply don't execute their instructions. There's no performance penalty for skipping work. The pattern we learned today, get thread index, check bounds, then execute, is something you'll use constantly. It's muscle memory for GPU programmers. As the puzzle notes, boundary checks get more complex with 2D and 3D arrays. We'll explore those patterns in future puzzles, especially when we learn about layout tensor and puzzle 4. Congratulations! You've completed puzzle 3 and learned the essential pattern of guarding memory access. This is a fundamental building block. Every kernel you write will use this pattern. Next up is puzzle 4, where we'll learn about layout tensor, which provides more elegant ways to handle array shapes and boundaries. If you enjoyed this tutorial, please subscribe to the channel to follow the entire series. We're building your GPU programming skills one puzzle at a time. For technical questions and community discussion, join us on the Modular Forum at forum.modular.com. The link is in the description below. The community is incredibly helpful. We'd love to see your solutions and answer your questions. Keep coding, and I'll see you in the next puzzle.